sure as an eclipse expert, now remember definition of an eclipse expert is you've seen one eclipse. You've probably gotten the question from people, is Earth the only place you can see an eclipse? And some people will give you an answer that's very vague. Others will say, of course we're the only planet that can see an eclipse. And some will go very religious on this topic actually and say, well, this is a sign of intelligent design and things of this nature. And I was asked this question by numerous reporters from different magazines that wanted to know how unique an eclipse event actually is. So I actually said, well, is it true that there's only Earth sees solar eclipses? Well, of course not. We've all seen the result of an eclipse on Jupiter. Probably looked through a telescope and seen a transit of the moon's shadow going across. But are those really good eclipses? So the question came up as to what is a good eclipse? A good eclipse is a perfect fit, like we see here on Earth, where the size of the moon, the size of the sun in the sky as we see them are equal, or roughly equal, enough so that we can experience the total solar eclipse. So now, the question came up in my mind, are there any other moons in our solar system that might possibly match this? And I'm looking for a perfect fit. So, definition of my idea of a perfect fit is it would be total or angular as viewed from the planet with one of its moons in orbit. And these are words I learned on this project, periapsis and apoapsis, when the moon is closest and furthest in its orbit. So I was looking for any circumstance where we would find a total eclipse at periapsis and an annular eclipse at apoapsis. I hope I'm pronouncing this right, I just been guessing at the pronunciation. So the first consideration is just how big is the sun? Well, from the Earth, the sun is approximately 30 minutes of arc size in the sky. And when you look at the other planets going further away, of course, the sun is going to get smaller. And this means that a smaller moon is going to be needed in order to produce a perfect eclipse. With the idea being, again, total or annular. It could be either one of them. So the human eye, as I found out here, can see approximately 1.2 seconds of arc, or about 0.02 degrees. That's about the best resolution you're going to see with the eye. So anything further away, and as you'll notice over here, the planet Uranus, we should be able to see the disk of the moon, or the sun. Neptune, same thing. We should be able to see the disk. It'll be small, but we should be able to see it. Pluto, we're getting down much, much too small now to really worry about it. So I said, I'm going to look at the moons here where we actually have a chance to see this and come back this direction. So I'm going to only study the moons around these planets, and I'm not going to worry about these because it would just be a dot obscured by a dot. And that's certainly not an interesting eclipse, especially if we're talking about an annular eclipse. So I went on the NASA website, and I said, how many moons are there out there? And they said there's about 180 known moons at the time when I did this study. I guess another 20 or so have been discovered since. But they were real small, so they're probably not going to work anyway. And so I ended up selecting a subset of those only from those planets. So I was not looking at large asteroids, I did not look at Pluto and others. Just wanted to see what was available from the larger planets. So I went off and I grabbed hold of the information, and you can get it also from this website here from NASA, that tells you all the planetary facts, all the moon facts that they have accumulated over the years. And I was looking at approximately 141 moons. Now normally this would seem like a rather difficult task and a lot of computational work. Fortunately, I'm a computer hacker. And as a computer hacker, that means I'm going to write a computer program to solve this problem for me. All I wanted was raw data. So I pulled all the data down from the NASA website and started to build a computer program that would allow me to do this. So basic data that we've got up here, these are the planets that we're interested in, Earth through Neptune. And you can see how many moons were studied for each one of them and roughly what the radius of the planet was. Because I can't do it just from the center of the planet. It's got to be from the surface of the planet. which poses an interesting problem for Jupiter and Saturn and Uranus. They're gas giants. So where's the surface? And I said, well, if you're going to watch an eclipse from those planets, where are you going to watch it from? Above the clouds. So we'll just use the radius out to the edge of the clouds as we see with the different planets. So those are the sizes that I managed to get off again, the NASA website, and decided that we're going to go forward with that information now to see how far away the sun and the different moons are and get their sizes. So the hacker went to work, started working on a computer program to compare just the angular sizes. I was not looking for detailed circumstances yet, I just want to do a simple comparison. I was going to look at the distance of the sun at perihelion and also at aphelion to determine what are the maximum and minimum sizes that the sun would appear, and also at each moon at its parallaxis and apoapsis. So I can now look at the range. Because if it showed an angular at one and a total at the other, then that's a good candidate for a perfect eclipse. So the angular sizes were all I was comparing. I was not looking at orbital parameters beyond the distances that they were from those particular host planets. Just the size ratio. So I want to see in the condition where the sun is smaller, the moon is the largest, check the condition where the sun is the biggest view and the moon the smallest, to try to figure out which ones would work. So I just simply divided one into the other to produce a ratio. A ratio greater than 1 meant that we had an annular eclipse event. A ratio less than 1 meant we would have a total eclipse event. So now, to match the Earth, the ratio of the sun and the moon angular size. Ratio is greater than 1 when the sun's biggest, ratio is less than 1 when the sun's distant. And here's the initial results from that program. Now at the very top, you can see that the Earth and the Moon, when we come over here to their ratios, and the ratio of the sun divided by the moon, there it is, less than 1 and greater than 1. So there's our annular and our total solar eclipse circumstances. What other possible moons out there might produce something that's even close? This list only shows the ones that I said were the most interesting. Or how close did they come? Actually, this is the full data number. And now you start seeing these ratios over here are very different. So we have some where the size of that moon is very small relative to the size of the sun. Others the other way around, where the size of the moon angular size is much greater than the angular size would appear for the sun at that distance. And I started to put, just to save myself time, color coding the books. I'm sorry, I jumped ahead. Color coding the results. So that if I actually came up with something that was a perfect fit, I put it in one color. And if it was kind of interesting, I consider this an interesting eclipse. In other words, I would be able to see something kind of cool with that relationship. And I began searching through the entire list there to try to find the ones that were going to match up the best. And I found a couple of them where you can actually see an annular eclipse under one circumstance and a total solar eclipse under another. So when someone says the Earth is the only place to see a total solar eclipse or an eclipse like we see here, that's actually not true. And mathematically it works out. And we can see it with these moons of Saturn. And you can see here that the ratios actually worked out proper so that we can go either side of it. Now obviously observing from Saturn presents its own difficulties. But if you live on Saturn, I suppose you know how to deal with these things. So now, I did find the Earth-like eclipse conditions for 3 different planets. Obviously, the Earth and the Moon, Saturn and Epimetheus, and Saturn and Pandora, which was kind of ominous, I should say. I was wondering, was I opening Pandora's box with this study? Because I had been asked the question, is this a sign of intelligent design? Am I going to get in trouble with these same people by putting this out? And I felt that that Pandora thing was like, is that a subtle sign saying, watch it, be careful where you go with this? All right, let's look at these other moons. Epimetheus, going around Saturn. It's only a 72-mile diameter. It's potato-shaped, with its longest axis is actually, or longer axis pointed back towards Saturn. And this has to do with basic gravity and orbital mechanics. Over many, many, many years, the heavier part of the moon ended up facing directly back at the planet itself. Now imagine this, it has a 17-hour orbit. It takes 17 hours for that moon to go around Saturn. Saturn is not small. Saturn's a lot bigger than we are. So that moon is really moving. It's moving at about 21 seconds of arc per second, which means that the size that we're seeing at it, the timing from contact 1, C1 to C4, approximately 15 seconds. That's a quick one. And it actually turns out that Epimetheus and Janus are an interesting combination of moons in Saturn. They share the same orbit. And Janus is a bit bigger, so it's always a total solar eclipse. It doesn't do an annular. But I thought it was intriguing to find the fact that these two satellites are almost in a dance, a cosmic dance going around Saturn. And they switch orbits. So at one time, Janus will be in the orbit of Epimetheus, and then other times they'll switch back and forth. And so I thought that was kind of interesting, but also the fact that the C1 to C4, 15 seconds, that's a whole new level of eclipse chasing when it comes right down to it. And I guess the computational work would have to be very precise to be in the right location for it. The other moon is Pandora. Pandora has a 15-hour orbit. That's even faster. It's only a 50-mile diameter moon, and it's oblong, also potato-shaped. And actually, it turns out it's not a very good fit. John Irwin was kind enough to go ahead and create a simulation using his tracking software. And down here on the bottom, you can see how it would fit against the sun. So we would never actually see a very good eclipse here, even in the total phase here, where it's total across here, but obviously the sun is shining through up here. So talk about double diamond rings for a fraction of a second. So the results. Did I jump in? All right, the results that came up. And I thought this was also an interesting statistic to share. Extreme totals. That's where the moon was over 2 times the size of the sun. You wouldn't see much of the corona unless you have really good optics. So I found 31 moons produce an extreme total, but 107 of them are extreme annulars, where the annular size of the sun is 2 times the annular size of the particular moon. So it's more common to actually see an annular eclipse than it is to see a total solar eclipse in our solar system. So now it's trying to find, well, okay, number of interesting eclipses where the moon appears less than twice that size, allowing for a view of the corona. And there were a couple of us on SEML that went offline and tried to debate on what makes for an interesting eclipse. And we decided anything less than 2 times that size would actually be able to see the corona, and hence it's an interesting eclipse. So we found 8 of those that would actually fit within that parameter, but still only 3 of them made the perfect fit. So of the 141 moons I tested out, 22% were totals only, 76% were annulars only, 6% were interesting, and only 1 was the best. There had to be a cartoon. You knew it was coming. I don't know. When I was doing this, I get inspired to draw these cartoons. It's a great way to take a break from computer programming. But yeah, the Earth has the best of all the best of the eclipses. Our angular size is the biggest. The duration is long enough that you can actually sit there and get bored from C1 to C2. Actually, you know that relative eclipse time, right? The hours. C1 to C2, that's hours. C2 to C3, 8 to 15 seconds, always. No matter how long they tell you it is, that's how long it seems. And then, of course, C3 to C4 doesn't exist for most eclipse people, because you saw totality, that's all that matters. So I went online and I looked around to see if there had been any other research done like this. And guess what website I found? creationresearch.org. And they came back with a thing saying that no, Earth is the only one that sees a total solar eclipse. End of story, no further analysis required. It's a sign of intelligent design. I wrote a letter, or an email actually, to the author of that article, and got an interesting response. 2 words. First one, 4 letters, starts with an F. So even though that was the, you would think they're very nice people and everything else, he did not like the fact that I had proved his study wrong. And why? His study was a non-study. His study was, well, obviously. And to me, it was like, well, everything that appears obvious is not always obvious, and it's worth looking into a little bit further. And I was actually surprised to find that nobody else had done this simple experiment. The programming work itself was less than a day. The playing with the data and debating with John Irwin and a couple of others about the validity of what I was looking for, it was a couple more days. So it really wasn't that difficult to figure this out, but it was interesting. I thought it was fascinating enough to say, hey, I'll do a talk about this at the Solar Eclipse Conference. And that's what I had to say about this subject. And I'd welcome any questions anyone might have. And I promise I'd be well within the time frame.
Yeah, well,
I didn't push this right to the left, but we got a few questions. Okay.
You talked about eclipses in our own solar system. Do you have any idea if the possibility, the chance would be to see solar eclipses in other solar systems?
Okay, the question is basically, what's the chance that we would see a solar eclipse in another solar system? Well, first problem we have is we have no data yet. So I'm going to say, yeah, sure, why not? When you look at the percentages, and the 6% out of 141 moons looked at were interesting. 3 of the moons showed that we do have a nice matchup. So the probabilities are in favor of having total solar eclipses in almost any solar system that contains moons and planets. There's a good chance we'll find them. And I look forward to the day when we have the international or intergalactic eclipse challenge. Which planet in the system that we can visit has the best eclipses? And I do have cartoons on that subject, but you'll have to go to my webpage to see those, because they tend to be a little bit racy.
Long time ago, I read a paper that somebody tried to look out what are the possibilities of seeing a solar eclipse by one Jovian moon observed from another Jovian moon. I think it was Isaac Asimov who mentioned that in the book, and I think there was some good cases found. You can actually stand on the solid moon of Jupiter and have an nice eclipse by another moon.
And that's very true. I didn't actually include that in my studies. This was just a preliminary study to see if what would be visible from a planet, not from one of the moons of the planets. But later on, I did go back and look at it, and from Jupiter, yes. Some of the Jovian moons do produce a perfect eclipse, but now the other moon's got to be behind Jupiter. So you've got to have it would actually be probably a very interesting sight, because you would have in the foreground Jupiter as kind of a crescent, and then you would see the eclipse beyond that, from that other moon. And the same thing on Saturn. I found a couple of them on Saturn. The thing is, what I found with the case being the moon, the sun is small. As you get further away, the angular size of the sun is small. Hence, the eclipses are quicker. Thus, I stand by my argument that the best ones are here on Earth. Yes, next. Go ahead.
So I just had the same comment as Daniel, but I have another one for you. It is the best for 2 other reasons. First is the rest of the outer solar system in front of Jim's got one square, so the sun is brighter and of course larger as well. So we do get the best, there's no question about it. Just to follow up, the exoplanetary systems, there's evidence now for systems like TRAPPIST-1 that have half a dozen Earth-like planets, that they're outside of each other's hill radii, so they can support moons and they're likely to go planar orbits. So make them up, Bill, and let us know what the possibilities are.
We can make up data. And as a computer guy, we get accused of that all the time anyway. But to be honest with you, I really just was curious about our own solar system in this particular study. And I'm sure as space exploration continues, we will find more and more planets. And I look forward to the day for the intergalactic eclipse contest. I hope to be there for that. And then if you find out another place has better eclipses than us, how many want to go? I would also like to see an eclipse like of a red giant. I think that would be a very different view of things too. Yes.
So I wondered, did you go as far as calculating whether you, because they're so quickly to orbit, could you get two in a row, like two orbits in a row to give you an eclipse because it's a little off?
Yeah, because you're only waiting a few hours for it to get around there. Actually, yes, but you would have to reposition on the planet because the orbits are not completely linear. Okay, so they are a little construed. And what happens if, like, Epimetheus and Janus have flipped orbits during that time? Now you've got to maybe wait a little bit further. And since you're already traveling on the surface of the clouds, how hard is it to take your rocket and go to another location and maybe catch up with that? As I say, a whole new definition of eclipse chasing comes to play. I don't think they're any good better than what we see here. I still think we win in this solar system. Anyone else? Yes.
So if I understood right, I think, correct me if I'm wrong, I think you assume basically the eclipse is essentially at midday, but if you're on a big planet and it's essentially at sunrise, I think the moon effectively would be a lot further away maybe, and then you have more chances of eclipses.
That was one of the refinements we made to the program. Initially, we did exactly what you're saying, at midday on the nearest position to the sun. So we added that, we said, well, let's subtract the radius of the planet, and this would be up in the pole. So now we are looking at the range between both. So on, I think it's Epimetheus was one, where up near the poles it would only be an annular, and you get the total as you get down closer to what we'll call the equator.
So you did take this?
Yes, I did.
Okay.
As I say, I opened the question up on SCML, and it's interesting some of the responses you get from people, and a few others were very interested in pursuing this study further, and I said, okay, it's written in PHP, it's up on the web, here's the source code, where do you want to go with this? And they turned it back to me and they said, no, you're the hacker. I only have suggestions. John Irwin, on the other hand, he's also a hacker, and so we played back and forth with this quite a bit. And when we found one that we thought was a perfect fit, that's when we said, okay, let's take the shape as we know it would appear and see what it really looked like, and ran it into the occultation software. And you saw the oval kind of footballish shape, rugby ball shape against the sun. And we decided, nah, other than the big diamond ring, that wouldn't be too cool. It would only last 0.4 seconds. Totality would be 0.4 seconds. Maximum totality, we calculated as being just shy of 0.6 seconds. So if you're going to try to add up to see an hour of totality, that's going to be a lot of eclipses to go to. Yes, sir.
Do you think that eclipses like Earth are a requirement to development of intelligent civilizations?
I'm sorry, you'll have to repeat that again.
Do you think that eclipses like on the Earth are a requirement for the development of intelligent civilization?
Oh boy, now you're back into that creation science guy. Because after his two-word response, I responded back to him with Jamaican. And basically told him what he can do. And then I said, does this prove intelligent design? No. Does this prove intelligent life might be there? Well, now we got into an interesting debate. Intelligent life likes total solar eclipses. Here we are. We like to talk about these things. We like to see them. So would it spur intelligent life? Would an amoeba see an eclipse and go, I gotta get smarter? I don't know. Obviously, that's a philosophical question, a theological question. And I am no philosopher and I am no theologian. I am a computer programmer, the worst of all the world. Yeah. Lawyers are below that, yes.
The moon is moving away from us. How long can we still see total solar eclipses?
Well, okay, the moon's moving away very, very slowly, and Glenn, you need to help me out. 2,000 years, we figured?
No, 700 years. About 600,000.
600,000 more years. Are you going to try to stay for that one too, the last total? And that would really be sad, wouldn't it? To be there for the last total solar eclipse on Earth. Because it's only going to be a fraction of a second. And it was, what's that? Would it be a transitional or a hybrid? Well, you know what? At that point, I would say it's the last. And at that point, who cares if it's transitional or a hybrid or what name they have to it? It's the last one. And I feel sorry for those that might be here during that time because they didn't get to enjoy what we have seen. Because what we have seen is truly wonderful. Yeah.
So we don't only live at one spot, but at one time.
I'm sorry?
We only live at one time.
We live at the best time for solar eclipses. There's other issues, of course.
And speaking of time, we have time for one question. And the final question is first. About, just maybe come back to the question of the other quiz. I think it was around 650 million years instead of 650,000 years.
Okay, so 650 million years to wait for the last solar eclipse. Personally, I'm not going to stay for that one because I think it would be a very sad eclipse to be there to say this is the last total solar eclipse. Now, with luck, we'll have space stations. And from the space station, you could say the Earth has grown. And you know what a Dyson sphere is, right? What if we built Dyson spheres where we could have our own solar eclipses every day? So, it could be fun.
Question, did you take into account also the angle of the orbit and the
okay, yeah, good question. Did I take into account the inclination of the orbit? By definition, almost all the moons are within the same orbital plane as the solar system. So yes, kind of. Did I actually look real closely at it to see where it might fall on the planets? Not yet. If the creation organization is willing to fund me, I will be happy to come up with a more thorough investigation on this subject so that they can use it in their publications to promote their concepts. All right, thank you very much.
Okay, thank you.